learners use compounds A to C, shown in the table below, to investigate a factor which influences the boiling point of organic compounds. 2.1. Which one of the following compounds, A, B, or C, has the highest boiling point? Okay, so let's do this. So looking at ABC, I can see that everything is the same except the chain length. So for A, I have 1, 2, 3, 4 carbons. For B, I have 1, 2, 3, 4, 5 carbons. And then for C, I have 6 carbons. Okay. So the one that is going to have the highest boiling point will be the one with the longest chain. And this is simply because there is an increase in the strength of the intermolecular forces with an increase in chain length. So this is going to be C. 2.2. For this investigation, write down the independent variable. What are we changing? The chain length. Whatever it is that you change during the experiment is the independent variable. 2.2.2. The dependent variable. What is being affected due to the change that we are making? So we are investigating a factor which influences the boiling point. So the boiling point is being affected due to the change in the chain length. So this is the boiling point. 2.3. Write down the type of van der Waals forces that occurs between the molecules of compound B. Okay, so this is going to be the London forces. It's the London dispersion forces. 2.4. How will the vapor pressure of 2-methyl pentane compare to that of compound C? Write down only higher than, lower than, or equals to. Okay, so we have C there, and then we are given 2-methyl pentane. 1, 2, 3, 4, 5. That's for pent. And then on carbon number 2, I have a methyl group. Okay, and then for C, we can see that C is linear. So it is just a hydrocarbon with 6 carbons. And then let's just say 2, 3, 4, 5, 6. And then we have hydrogens there. Okay. So one thing to notice is that CH3 group, it is a side chain. So it means that this C will have stronger intermolecular forces. Because remember, we said that branching does what? It reduces the strength of the intermolecular forces. So it means this will have a higher boiling point. And then the boiling point for this one will be lower. Okay. And then we know that the boiling point is inversely proportional to the vapor pressure. So whenever the boiling point increases, the vapor pressure is going to be lower. How will the vapor pressure of 2-methyl compare to that of compound C? So it will be higher than, because the boiling point is low, higher than, and then 2.5. The learners now compare the boiling points of compound D and E, shown in the table below. So we are given an alcohol as well as a carboxylic acid. Okay. So how does the boiling point of compound D compare to that of compound E? Write down higher than, lower than, or equals to. Okay. So this will represent this part right here. Okay. So we have an alcohol, which is our D, and then we also have a carboxylic acid. Okay. So what happens here is that this pi bond can shift and then transfer the electrons to the oxygen. So this is going to look something like this. Okay. So this oxygen is negatively charged, so it has the ability of attracting hydrogens. So it means that for the carboxylic acid, I have two sides for hydrogen bonding, whereas for the alcohol, I only have one. Okay, now let's answer the question. How does the boiling point of compound D compare to that? So it is lower than. And the reason for this is because E, which is the carboxylic acid, has two sides for hydrogen bonding, while the alcohol, which is D, has only one. And then the strength of intermolecular forces increases with an increase in the number of sites possible for hydrogen bonding. So this simply means that E, the molecules of E will require more energy to be separated. Thus, we'll have a higher boiling point.